When the Apollo program took us to the moon, it changed our perspective forever.
Roger, 0G, and I feel fine. Capsule is turning around. Oh, that view is tremendous.
For the first time, we were able to admire Mother Earth from a distance. This image made us realize that our blue and white planet is a unique part of cosmic space. As telescopes extend our outlook far beyond the solar system, we begin to realize that our world is unavoidably part of a stormy and creative galaxy. A new perspective is emerging. The galaxy drives our climate system in ways that we are only beginning to fully understand. For more than a decade, the Danish physicist Henrik Svensmark has worked on a new theory about the climate. This will alter our understanding of climate change.
The processes that takes place in our universe, from exploding stars and also dramatic changes in solar activity, are affecting us much more directly than we ever dreamed of.
Over the years, we have followed Svensmark in his struggle to be heard in a climate community resistant to the idea that present-day climate change might have natural causes.
The fact is that clouds and water vapor have the biggest greenhouse effect on the Earth's climate.
The secrets are to be found in the everyday clouds in our sky.
In times when everybody is talking about CO2, clouds are a really important factor of climate change. Without clouds, the climate on Earth will be completely different, and just small changes in the Earth's cloud cover will change the Earth's climate. So understanding clouds is a very, very crucial point. The mere idea that processes in space and not just processes on Earth is important for climate, I think is deeply fascinating. In 2005, we actually found experimental evidence that the Sun and the galaxy is determining climate here on Earth. But for some reason, no scientific journal wanted to publish this. It was a big disappointment for me and my team.
There is a problem that has always been with us. New ideas are rarely welcome. In science, where particularly some young person not known in the field proposes some radical new idea, he may experience great difficulty in getting it published.
The bottom line seems to be that instead of thinking of clouds as something being a result of the climate, it actually sort of upside down. It is that the climate is a result of changes in the clouds. The first time I got an idea of how important clouds could be on the Earth's climate was when my boss, Eichel Friis Christensen, made a discovery where they found a beautiful correlation or agreement between solar activity and the Earth's temperatures. The agreement was so good that it could not be accidental. And this was really a big inspiration for trying to understand and trying to use clouds as part of that explanation.
When we published this in 1991, it was at a time where everybody believed that the warming that had taken place during the century was mainly due to carbon dioxide increase, man-made greenhouse gases. So when this community saw this nearly perfect correlation between solar magnetic activity changes and temperature, they were very surprised. What we could see was that when the magnetic activity of the sun was larger, then the temperature on the Earth was higher. Nobody had an answer to what kind of mechanism could be the cause of that.
We knew that somehow the magnetic activity on the sun had to have an influence on the Earth's climate, direct or indirect. But how this would come about was a real scientific mystery. But one day, someone stepped into my office and mentioned cosmic rays. When I heard this word cosmic rays, it made me immediately think of an experiment I did in high school where we had what is called a cloud chamber. Inside the cloud chamber you have supersaturated air, and when a particle, for instance a cosmic rays, go through, it makes a string of small droplets like a small cloud. With this image in my head, I thought, what if cosmic rays are responsible for forming clouds? And what if the sun with its magnetic field is capable of changing the clouds on Earth? Then we would have a perfect explanation on how the sun will be responsible for climate through our everyday clouds that we see on the sky. You cannot see or feel the cosmic rays, but they are let loose whenever stars die in supernova explosions. As atomic particles with enormous energy, they rush through the galaxy at almost the speed of light. And some of them bombard the Earth. But the sun fights the cosmic rays and controls just how many hits the air. In order to find out if cosmic rays affected clouds, I began to look for data. I collected satellite data of the variation of clouds in the atmosphere and compared them with variations in the cosmic ray intensity. There was a beautiful, clear-cut correlation that surprised me more than I ever dreamed of. The red curve is for the cosmic rays, you see the variation, and the blue curve, that's for the cloud cover. It means that cosmic rays are affecting the Earth's climate, and that's a fascinating thought, since it means that space is very and directly relevant for us. The magnetic field that comes out of the sun has more than doubled over the last 100 years. As a result, fewer cosmic rays have sprayed the atmosphere and fewer clouds has formed. The consequence has been a warmer Earth. When a strong magnetic field comes out of the sun, fewer cosmic rays spray the Earth. That means fewer clouds to keep us cool. But a lazy sun with a weak magnetic field lets in more cosmic rays from the stars. And in the air, they make more clouds. That's how the stars and the sun controls the Earth's cloudiness.
The suggestion was made by Svensmark in Denmark that this effect of cosmic rays is really important, and he based that on the remarkable correlation between worldwide cloud cover and the cosmic ray intensity. The magnitude of the effect, if his speculations are correct, would suggest that that is as powerful effect as the present greenhouse effect or the brightness variations of the sun. It remains to be seen now, of course, as to whether that effect is valid, but it is a major contributor to this whole process that needs to be investigated very carefully.
This idea with the cosmic ray modulation of the cloud cover is probably the most interesting mechanism today. If that was a building, and what is found in this research results from Denmark is that there's a very good correlation between clouds and the cosmic ray modulation, which we have measured for 50 years almost. But this shows that it's the sun's magnetic field that's very important for how the sun appears, and that's very important to understand one cycle, and then we can go back and try to understand how the sun has changed on the long term. We know now that the sun's magnetic field have increased, and we know the sun is more and more active. The activity has been increasing the last 100 years by a factor of 2. If Svensmark's work is confirmed that he's right about this idea, I think it will have big effect on the whole climate discussion, because the clouds are so effective in changing the climate or trapping or closing out radiation. It's now important to do the research to try to understand this mechanism. And so I think we should take this very seriously and try to understand this mechanism.
When we presented our results in Birmingham in 1996, we were of course very excited to present the results, but much to our surprise it was received very, very negative. And the only thing we had done was to present a scientific result which showed that the sun through the clouds might be very, very important for climate.
There was, of course, a reaction also from the International Panel on Climate Change, the UN panel. Bert Bolin, who was the chair, scientific chair at that time, he thought it was irresponsible of us to say that something else than the CO2 could be the main driver for climate.
So there's no doubt that the sun has an effect on climate.
The whole climate community really hated the idea that the sun should have a major impact on climate. That was seen as a disaster. I was actually shocked about the responses that we got. During the last 25 years, CO2 has been the dominating theory trying to explain all climate variation. However, if we look at historical climate, there's absolutely no doubt that the sun has been extremely important, and you cannot ignore it.
We're at the Dead Sea, and we're going to a place called Nachal Batzim, which is one of the nicest places where you can see climate variations taking place here. people have this conception that the sun is this constant ball of gas that doesn't do anything. This is wrong. In reality, the sun can sometimes be very active. It's this solar activity, this dynamic nature of the solar activity, which affects the solar winds and which affects the cosmic rays and which eventually affects climate here on Earth. Climate variations over the past decades, centuries, millennia can be reconstructed from many different places around the world. Here we're now located in the Dead Sea. 20,000 years ago, the Dead Sea was higher, it was much wetter, and the level was higher than where we are standing. And every year there were yearly deposits which were left on the lake's floor. And here we can see those annual deposits. Basically, during winter, the dark deposits are left, and during summer, the bright deposits are left. So the ratio between the dark and the white bands tells us a climatic story, tells us how the climate here varied during the years. On these timescales of centuries and millennia, you can reconstruct what the sun was doing using cosmogenic isotopes like carbon-14. What's interesting is that this carbon-14 is directly formed by the cosmic rays. So this and other results or other measurements from around the world tells us that the sun is affecting the climate. This link between solar activity and climate on Earth, it's not hypothetical. You just see it in the records. When the sun was more active, you indeed see that it was warmer on Earth, and vice versa. "300 years ago, for example, the sun was not very active, and we were in the height of the Little Ice Age when it was cold in many places on Earth. 1,000 years ago, the sun was active. It was as active as it is today, and it was warm everywhere. The Vikings could map all of Greenland because the northern shores of Greenland were not frozen. Most of the people today think that most of the climate change is because of CO2, but this is wrong. Most of the warming over the 20th century is because of the sun.
If we look at Earth from space, we will see that about 60 to 70% is covered by clouds. If more cosmic rays comes down, we will have slightly more clouds. And you can imagine the opposite, fewer cosmic rays, we have a little fewer clouds. Instead of thinking of clouds as a result of climate, it's actually showing that the climate is a result of the clouds, because the clouds take their orders from the stars. After we found the link between cosmic rays and clouds, we only knew that it was a total cloud cover, but I had to find out what type of clouds. And at some point it became possible with a new data set to investigate exactly this. And at that time I got help from Nigel Marsh.
Yeah, I sent that figure to her.
He helped analyzing these data.
The one you asked me to.
Great.
And much to our surprise, we found that the link is actually to the low clouds. So it seems as if cosmic rays are changing low clouds.
All right, I'll speak to you later. Yeah, bye. Bye.
And that is very, very good news for the whole idea.
When I got this result, I thought the correlation was much better than I ever dreamed of.
If you decrease the amount of low clouds, it will be more heating down to the ground. And in particular now, this new work that they show that it's only the low clouds that changes, which makes it very interesting. There's still a mechanism to explain this that's missing. And it's now important to do the research to try to understand this mechanism.
There's a fairly large fraction of low clouds, a large part are responsible for a large part of the cooling caused by these clouds.
The reason low clouds are so important is that they actually reflect a lot of the sunlight back into space. I mean, we know them when we travel in airplanes. These are these monotonic scenes that we see over the oceans. And they are white because they are reflecting the sunlight back into space. And you can imagine if you change the amount of low clouds, you change the amount of energy that the surface gets. That means that low clouds have a strong cooling effect on the Earth's climate. So if we have more low clouds, climate will become colder. And if we have fewer cosmic rays, we have fewer low clouds, and the Earth becomes warmer.
You mean with the ISCO data set? It's in the infrared, what we've been looking at.
That's interesting. Okay. Well, I first heard about Henrik Svensmark's work when we became interested in looking at how aerosols, or very small particles, are produced in the Earth's atmosphere in the first place. I mean, this is important because all clouds are formed upon aerosol particles that are in the atmosphere.
So the satellite is looking at a specific parameter.
In terms of the work that we've done, what we've found is that the galactic cosmic rays are capable of modulating the aerosols, or small particles, in the lowest part of the atmosphere. In fact, we can show that the aerosols produced by galactic cosmic rays are significantly modulated in the lower layer, which contains these clouds that produce a cooling effect on the Earth. What we don't understand at this point is exactly how and why they're formed. Every cloud droplet that's formed is formed on a particle initially in the air. And so it's absolutely crucial to understand how these particles come about and what their properties are. Otherwise, we can't ever hope to understand clouds and their behavior.
And that's where cosmic rays actually might come in. Because what do cosmic rays do when they enter the Earth's atmosphere? They produce small ions. Oh yes. So it is the belief that these small charges help forming these small specks or aerosols in the Earth's atmosphere.
Whereas most people would think that since there's water in the atmosphere, that naturally there'll be clouds, but that isn't true. The only way that clouds can form in the atmosphere, in our atmosphere, under normal conditions, is to condense onto an aerosol or existing particle in the air. Every cloud droplet that's formed is formed on a particle initially in the air. All clouds are formed upon these aerosols. And so it's absolutely crucial to understand how these particles come about and what their properties are. Otherwise, we can't ever hope to understand clouds and their behavior.
In science, it's not enough just to have a good theory. You also need some experiments to support the ideas. I was very determined to get an experiment that could show that we had this connection between cosmic rays, aerosol formation, and clouds. What I'm going to talk about is cosmic rays. These are particles, or very energetic particles. They enter the Earth's atmosphere and we can actually measure them. So when we have maximum activity, you see that there's not so many cosmic rays coming in to the Earth's atmosphere. That's because now the sun has a very strong magnetic field, and it's difficult for the particles that come from the galactic space to get into the solar system. So there seems to be an agreement between changes in solar activity and changes in climate. So what is really needed is some experimental evidence that can say yes or no whether such a relation, I mean, how does it really work? That is what is needed. And it's very fortunate that such an experiment looks like will be performed.
I would like to say I think the experiment is completely misconceived and shows a complete lack of elementary knowledge about how clouds behave. So whichever way you look at it, that experiment is completely misconceived and will tell you nothing about what happens in the atmosphere.
Well, I totally disagree, but I should say that the people that are involved there are people that are experts in aerosols and atmospheric chemistry, so they know what they're doing. So, and I know, I mean, they will disagree with your point of view, but it's true there are different views, but you are one extreme, I would say. I've many times given talks where people have got very excited and very strongly trying to tell me that what I was doing was completely waste of time.
Have you read my book?
Well, I know of your book.
Well, there you are then. You shouldn't argue with me on cloud physics. No, the whole thing is a complete misconception.
Not a single one has come up with anything from a scientific point of view that made me think that there was not something, a real scientific question worth pursuing.
So, I mean, you know, what's the point of doing that experiment?
Well, there's been written several papers where they discuss where do the cloud condensation nuclei actually come from, how are they formed.
Oh, we know that.
No, it's not known, according to these persons.
Oh my God, well, they just must read the literature.
I had this theory, so I decided that we should do an experiment in Copenhagen that could show whether my idea was right or wrong. Unfortunately, it turned out to be much more difficult than I thought it would be. I mean, I actually started this without having no funds at all, and I just continued hoping that we would get money at some point. Building the laboratory, building the experiment, getting the funds, it actually took almost 4 years. The idea in this experiment is to investigate what is the role of cosmic rays. And the idea is that we in the end will be able to mimic the processes that are going on in the real atmosphere. So this whole chamber is built in such a way that we can control ions inside it, and we will be able to reveal for the first time how important ions are in the production of forming new aerosols and in the end new clouds. The motivation for doing this experiment has really been trying to understand why there seems to be this relation between solar activity and climate on Earth. All this political turmoil that is surrounding global warming and so on is irrelevant for the science. And the kind of experiment that we are doing, I think it's a necessary experiment because it will improve our understanding on one of the most important processes in the atmosphere, which is cloud formation.
Originally, I got interested in the topic when a colleague of mine in Germany asked me what are the effects of supernovae on life on Earth. And I decided to give him a serious answer. What I did, I looked at the literature and eventually stumbled upon Henrik Svensmark results about cosmic rays and cloud cover. So I realized that if this hypothesis is correct, that cosmic rays affect cloud cover and climate, what it would mean is that also variations which don't originate from the sun, but also variations from the whole Milky Way, they too will affect climates on Earth. Ever since I was a kid, I was interested in astronomy. That's why I became an astronomer. I never realized as a kid, I always appreciated this Milky Way, the fact that you can go out in a dark night and see this beautiful galaxy that we're inside of. It is something that we actually live in, it's part of us and it's affecting us. It's affecting climate here on Earth, and you must take it into account, into consideration if you want to understand past variations in the climate. What's fascinating is that this Milky Way, which looks something which is very far away, it isn't very far away. We are part of it. And this link between this Milky Way and us is cosmic rays.
The solar system moves in and out of the spiral arms. And the spiral arms are the regions where you have the new stars. And the new stars is also, some of them, the heavy stars that live very shortly and explode in supernova. That means that you have more cosmic rays as you move into the spiral arms.
If we look at the Milky Way from the top, what we'll see are 4 spiral arms, and that's because the Milky Way is a spiral arm galaxy. So we have 4 spiral arms. We are located here on some small armlets. We are rotating around the sun once every year, but the whole solar system rotates around the Milky Way once every about 250 million years. That's one galactic year. What this means is that every 150 million years, when we pass through a spiral arm of the galaxy, it's colder by something over the 5 degrees or 10 degrees. When we're outside of the spiral arm, it's hot. Now we're on this small spur, so we're witnessing cold weather. When we enter a spiral arm of the galaxy, we are going to witness more cosmic rays reaching the Earth, more atmospheric ionization, more cloud condensation nuclei, and therefore more low-altitude clouds, or to be more precise, whiter low-altitude clouds which better reflect the sunlight and cool the Earth. So the bottom line is that when we enter a spiral arm of the galaxy, we should expect lower temperatures. 100 million years ago, these cliffs were part of the floor of a warm ocean. Earth back then was between spiral arms of the galaxy. All over the Earth, it was much warmer. We had dinosaurs sunbathing in Alaska or in Antarctica. About 70 million years ago, we started approaching and entering the Sagittarius spiral arm, and Earth became exposed to a higher flux of cosmic rays because of all the stars around us. This larger flux of cosmic rays was responsible for the formation of more clouds and colder conditions here on Earth. The ice sheets that later formed, they actually pushed all those cliffs out of the water like bulldozers, and they rippled the landscape. So what we see here in these cliffs is a good example for hot conditions on one hand when those cliffs were formed, and cold icehouse conditions which we have today, which are responsible for the uplifting and current conditions of these cliffs. It may sound strange to most people that we're talking about icehouse conditions today, but if you look on the long time scale, you find that during most of Earth's history, we didn't have any ice caps whatsoever. Today we have. 450 million years ago, we had very cold conditions here on Earth. However, we had more than 10 times as much CO2 in the atmosphere. So clearly CO2 is not a major climate driver, at least it wasn't a major climate driver then.
When we talk about climate changes on these timescales, it is a kind of climate change that is much, much more dramatic than anything we have seen in our history. When we are in between spiral arms, it looks as if we are in a warm period called a hothouse, and most of the ice is simply melted. There's no ice at all. When we are in the spiral arms, half the area of the Earth is simply covered with ice. And the changes in climate, I mean, are much, much more dramatic than anything we have seen recently.
Over the past billion years, Earth has passed through periods when it was cold and periods during which it was hot. And lo and behold, the periods during which it was cold synchronized with the astronomical data, which tells us when we should have passed through spiral arms of the galaxy. At some point, I realized that you can actually reconstruct the cosmic ray flux, and you can do it with these things, with the iron meteorites, because iron meteorites, after they break off their asteroids, they are exposed to cosmic rays, and they record the cosmic rays in the solar system over hundreds of millions of years. And what you find is that this cosmic ray flux changes exactly as you would expect from the astronomical data on one hand, and it also changes exactly in sync with the climate variations that you can reconstruct using geological record.
I've been working almost all my life on issues related to environment. And of course, one of the biggest problems and issues was what was the climate and how the temperature of the seawater changed. And we worked on the fossils like this, called brachiopods. These shells record the temperature of the past oceans. When they form, they reflect the temperature of the ocean water because they build in the atom of oxygen. Then you could measure this proportion of oxygen, and you could get a measure of the temperature of the past oceans, and that means of the temperature of the Earth and climate. So when we can measure this, we would get a record of ocean temperature for 500 million years. When I look at the data, I realized that actually there were some oscillations in the general trend of temperature, and that those oscillations fitted quite well with what we knew from geology, what kind of a climate was at that time. Working with the colleagues, we did an evaluation and statistical study of that, and we saw that there was some kind of a periodicity roughly over about 140 million years, switching back and forth between hothouse and icehouse. I suspected that the reason for this rough periodicity was something to do with the sky. But I was searching for it and couldn't find anything. So essentially I gave up. I didn't have an explanation.
Veizer, he reconstructed the temperature using geochemical records. And the difference between that reconstruction and what I was using is that Veizer actually reconstructed the actual temperature. So he knew exactly how warm it was and how cold it was. So I emailed him.
One evening, I was sitting in my office working. Suddenly, an email popped up, and this was near Shaviv. And he says, well, I may have an explanation for you. He was telling me that he was working on cosmic rays variability over the more or less the same time intervals, and that the variability in the amount of cosmic rays hitting the Earth over this time interval was more or less similar to the variation in those oxygen atoms or in the climate which we observed.
After I teamed up with Jan Veizer, we had an actual temperature reconstruction. And what we could learn was that it was colder here on Earth by something like 5 to 10 degrees when we were inside spiral arms of the galaxy. Nobody found anything like that before, and we were simply amazed from it. But more interestingly, what it means is that cosmic rays are the main climate driver on Earth, at least on geological timescales. And the only explanation you have for it is the Svensmark theory about the cloud cover. When you compare the geological record to the astronomical record, that's what you get. You see that the two barcodes give you the same product. The black line is the geological reconstruction of the temperature on Earth using the geochemical records of Jan Veizer. And what you see in the red is the cosmic wave flux variations. When both things are added together, they correlate very well. Statistically, it's very significant, but you don't have to believe the statistic. You can just look at it and realize that it's very meaningful.
It's been said so many times that the sun has not been responsible for the heating we have seen the last maybe 20, 40 years. However, if you look at the data, for instance, the ocean data, you will actually see that there's a very good agreement between temperatures and solar activity. And what you see is the temperature of the ocean down to about 50 meters. But if you compare the overall agreement with how the red curve is varying, it's very good. And the red curve, that is the cosmic rays. That is how the cosmic rays have been varying over this period. So we actually see even today that the sun is dominating the temperatures or how temperatures evolve. It has done so in the past, it's doing this now, and will also do it in the future.
An experiment like the one taking place here in Copenhagen is crucial because if successful, it will shed a lot of light on the physical origin of the link between cosmic rays and climate. And this will be the last piece in the puzzle which would make the picture complete.
So the effective aerosol background corresponds more or less precisely to what you have over the ocean. The experiment is not just something that you turn on and then you get the result. You get many, many results, and you do a lot of experiments, and you try to see if everything is consistent with that interpretation that you are giving.
The results of this experiment, hopefully we will know exactly how the sun affects climate, how it modulates the cosmic rays reaching the Earth, how cosmic rays control the amount of ionization, and how ionization controls climate, and through most probably formation of cloud cover.
It's very interesting after nearly 8 years of work that we finally got to this phase of trying to understand these experiments. All the bits and pieces was done over nearly a year. So it's not like from one day to another you all of a sudden jumps up and says, fantastic, we got the result. It's not like that. It's actually hard work. Don't you think? I mean, there's always a degree of uncertainty when you do experiments because you are constantly questioning everything you're doing, whether it's right and wrong. But we have been very, very careful, and we have done many tests on these ideas. So I think, I truly think that we have found a very, very important mechanism. And the mechanism was a big surprise how it actually worked. It's far. I mean, this is 0.34 ppb. Well, so it's very, very low. What we find when we mimic a higher flux of cosmic rays is that we actually produce more aerosols in the chamber. This actually means that cosmic rays are producing aerosols, and these are the aerosols which are responsible for forming clouds in the real atmosphere. Through our experiments, we have found a new form for atmospheric chemistry, which we think is responsible for the formation of new aerosols and therefore also for clouds in the Earth's atmosphere. And it shows that events in the universe are driving climate here on Earth to an extent that has never been understood before. A large part of the clouds that we see in the sky is really a result of this process that we have investigated experimentally. But of course, now we have to see how other colleagues react to our findings, and that will be very interesting to see how this work will be received. But I think we have done a very good work, and I'm very pleased that how everybody has been working on this project. So this is a culmination of many years of work. This is really nice. We thought we had a really scientific breakthrough in the understanding of how cosmic rays affect the Earth's cloud cover and therefore also the Earth's climate. But for very strange reasons, we could not get the paper published. I think we submitted it 4 times to different journals, and we still could not get these results published.
Henrik Svensmark and his group had very nice results, and I would have expected them to be published immediately, a few months after they found it. Instead, it took them 16 months to publish it, and the reason, I think, is because of reluctance of the climate community as a whole, in particular those who are supporting the anthropogenic greenhouse gas theory, to accept the idea that this new theory, which is already shown to be supported by a lot of empirical evidence, is also supported by experimental evidence.
The most frustrating part about the rejections was that there was no real critique that we had done anything wrong. It was things like, it's not interesting, it's too long. There was no real critique of the ideas, so therefore this type of rejection was even more frustrating.
Editors are sometimes remarkably naive about these things, but I think they really should look into these things, and when a negative report is conspicuously without substance, they should ask the referee to clarify it. This has a new dimension now that global warming is a political issue. Things become politically incorrect, and in the United States at least we have cases of good solid research on global warming being refused for publication because somebody has made up his mind that that isn't the way it is and you can't publish. I think this is not only unfortunate for the author, it's unfortunate for the country and the world as a whole, because this is a problem we had better get straight so we know what to do.
Finally, I think after more than a year of waiting, we got the paper published in the Royal Society. At the end of this journey, I can now say with great confidence, yes, we have found a very beautiful solution to the cloud mystery. And what remains a mystery is when the rest of the climate community will understand that far greater powers are controlling the climate from the outside.
The sun affects climate here on Earth. The Milky Way affects climate here on Earth. And if you want to understand what's going on, we have to take these factors into account. It's beautiful because instead of us living here in this isolated planet, we're part of this galactic ecosystem. We're witnessing what's going on around us.
These ideas are showing that the Earth is no longer just an isolated little island floating around in the universe. We are part of the big universe, and the processes that are going on there, like star formation on the long time scales, or changes in the solar activity, will all affect the Earth's climate. And it can have very large changes in the Earth's climate because of this.